distance. Not just distance, but perpendicular distance. The word perpendicular means 90 degrees. Now, look at this. Look at this and look at this. They are 90 degrees to each other. So that is the word perpendicular. So it means that the distance we are talking about is a distance that must be at 90 degrees. So when you multiply force and that distance, we have what we call what? Moment. Now this is how your forklift works. You know your forklift has tires, right? Yeah. And then it has the fork at the front, right? Then it has the back tire. Then there's what we call the counterweight. Right? The counterweight is usually made of your cast iron. The essence of the counterweight is that, okay, look at it now. This is the counterweight, right? This is the front tire. That is the fork. The essence of the counterweight is giving you opportunity to carry enough load at the front. This is what we call the fulcrum. This is what we call the effort. This is what we call the load. This is where you put your load. So this is a simple machine in physics. In fact, we call it first class lever machine. What I'm saying does not really matter. First class lever machine. Your wheelbarrow is a machine. You know, machine is anything that with little effort you can carry a lot of load. That's what machine is. So your wheelbarrow is a machine. You are carrying the wheelbarrow. The tire is the fulcrum also. But in that case, the load is at the middle. But in the case here now, it is your fulcrum that is at the middle. Your load is at the front. Your effort is at the back. So wheelbarrow is a second class lever machine, but our forklift that we are looking at now is first class other machine. So fulcrum is at the center. So at the end of the day, we have something like this. Fulcrum, the effort, the load. Your fulcrum, your effort, which is the counterbalance. Then this is where you put your load. So this is a simple diagram of our forklift plane. So what we are saying is that, I said moment, right? Mm-hmm. This effort is load now, so it's force times the distance. Let's call it L1. Let's call this L2 as the distance. Compared to load and the distance also. When we multiply this effort and the distance, we have the moment as a result of the counterweight. When we calculate the force of the load times the distance, we also have what? The moment of the load. Now, for our forklift to be stable, the moment of the effort must always be greater than the moment of the load. That is how we get our capacity. So there is the moment of the effort. That is how the capacity comes to play. You know, the distance is not something that you change. The distance is there already. You are not moving your counter weight forward or backward. It is there. So from there, we know the capacity of the load that we can get. Because this is known. The load of the counterweight is known. This distance is known by design of the forklift. This is also known. This is what we don't know. This is what we want to carry. So at the end of the day, whenever we put this, or everything here we adjust, the moment this exists, what happens? So that is the first part, which is balancing. Tomorrow we talk about stability. That the stability is, even though you are carrying the weight, as you are taking your forklift up, you can tilt. We look at that. If this is at times you have to carry a load like this instead of like this. We look at, there's what we call the distance, the radius. We look at it tomorrow, right? But just for today, I just want us to understand that the moment of the effort, which is the counterweight, must be greater than the moment of the load all the time. If not, what happens? It will tilt. So we are saying that the moment of effort must be greater than the moment of the load. So that is the physics behind what we can carry. So when you get to the forklift,